What's up, calculans? It's Alan. We're here at the last section of this first chapter of new material called calculus. The nice thing is there's not a whole lot new in this one. It's one that we could actually skip parts of. It's called the precise definition of a limit. And you're probably thinking to yourself, we've had so many definitions of what a limit is, and I got it. The x, whatever that a value is that we're approaching from both sides, has to have a y value that it's approaching from both sides, the same value, whether it's a whole or not. As long as it's approaching the same value, it doesn't have to be that value. That's actually continuity. And that's what we just went over last section. In this one, I'm going to introduce some stuff to you, namely the precise definition of a limit that's very, very, for lack of a better term, mathy. And for those of you that do plan on majoring in math or going on to a higher level of math, this is something that I at least want to show you. I'm not going to go into too much detail about it though, because that will be a smaller number of you than the whole course. And it's something that you will have to see pretty far down the road. So it's not something that you'll likely remember very well, if at all. So at least you'll have some memory of seeing it. But without further ado, let's get to the precise definition of a limit. And then we'll wrap up this section of limits and this chapter of all the definitions, laws, and rules for limits with one last thing, taking this to infinity and beyond. What we're going to talk about now is what a few of these symbols mean before we can give you that definition. So if we had a distance between 2 points, how would you find it? Let's take my point of age and your point of age. How would you find the distance between them? You'd have to subtract. The thing is, I'm most likely older than every single one of you. I'm not going to tell you how old I am, but if we took yours and subtracted from mine, then we'd get most likely a positive value, which is what all distances should be. However, if we did the reverse of that, then we might get a negative value, and therefore we should not have that. And the way we get around that is by throwing these absolute values around it. So then when we find the difference, which will give us the distance, always as a positive value. So we can do that with any two things, not just some random point A and B. So what if we wanted to know the y value and another y value? We'll call L. If we found the distance between those, and we said that it's less than some number, this is the symbol epsilon, another Greek letter. And that's going to represent a really, really small number. And we can do that also between x and a, rather than just some random 2 points A and B, x being the unknown or generic number line on the x-axis. And as long as they're not the same two values, then the distance between them can also be less than some other Greek letter we're going to call delta. Since they're not the same, then this cannot be a 0, where this and that are not the same and therefore cannot be 0. Right? And if we took our definition of absolute value, which the absolute value of any number less than some, say the absolute value of x is less than y, well, we know that that means it could be less than y or greater than negative y. So with that being said, then we can take that idea that we learned way long ago in algebra, and we can apply that to these types of symbols, where if it's less than epsilon or less than delta, we can squeeze it between the negative delta and the negative epsilon. And that's exactly what we do here. We then also add over the L to both sides and the A to both sides, so that we isolate our function, which is what we're concerned with. So that's a little bit of the algebra before we get into the calculus and give you that precise definition of a limit. So here it is very quickly. Again, just want to go over this, give you a little explanation as to what it kind of means, but you already know the definition of a limit in symbols is that. We're going to say, let every y be defined on some open interval that has some number a, except maybe at a itself, like we mentioned, can be a whole, but can still approach from both sides. And if we know that this is a positive value, some distance, and there exists another positive value, some distance delta, that when we take some x, any x, and find the distance between it and some other number we're going to call a, and it's between 0 and that delta, and we do the same thing with our y values, and it's less than the epsilon, like we just explained up here, then we say that the limits of our function as the x approaches the a is equal to that L. And you're probably thinking to yourself, that's just a lot of words for what we've already said the last 4 sections. And you're right. But again, this is that formal epsilon delta definition using those Greek letters, delta and epsilon, in a more defined and precise way. And of course, what helps us to see what all of that means? Here comes a graphical explanation to try to make this make a little bit more sense for you. So what is this all saying? Well, again, let's pick some a value. That's our x that we're going to be approaching. And as you guys know from both sides, and we're going to say that there's this little tiny value we're calling delta. And so how would we get a little to the right? We'd have to add it. How do we get a little to the left? We'd have to subtract it from a. And that's that gap, that distance apart we're calling delta. And if we plugged in those values, we're saying that if the limit exists when we approach a from both sides is L, there's our y value, our limit. Well, then if we plug this in, we'd get that. And if we plugged this in, we get that. And in order to get those values, we would say that, okay, let's call that gap from here to here, where this from here to here was delta. This one is epsilon. And so this little gap here from L, it's above, so it would be adding, and this one below, subtracting. And therefore, we have our scenario of, as we approach the a for our x on both sides, our y values, as that epsilon gets smaller and smaller and smaller, it approaches that value L. So the smaller we can make the delta, the smaller the epsilon will be, and therefore giving us our L. As you can see here, even closer, and here, even closer. So that's all this definition is meaning. Again, wanted you to see it. Don't worry too much about it. We won't do anything else with it in this course, but there are times that you may run across this down the road. You'll even have a course where you'll take, if you are a math major, and start proving why these things work the way they do. Okay? But for this one, I don't feel like it's that important for us to go into too much more detail with it. Let's continue on with the last thing for this chapter and this section. The good news is this is a concept that we've already discussed, and it is one in the extreme, which, as you know, limits, we've already pushed that extreme. Now we're going to go to the very ends. So if you remember, we've discussed this. It was concerning that of an infinite limit. But you got to be careful. It's not the exact same as the one that we've already discussed. It's something a little bit different. So there's 2 different variations that I don't want you to confuse as the same. So I put them here as 1 and 2 and tried to emphasize that the way that they are said does tell you what you are exploring. So be careful. The first one is limits at infinity, and the other infinite limits. So you can definitely tell a difference when saying it and writing it out, but what is the difference of what the process actually is for these? What do you think they mean by limits at infinity versus infinite limits? Well, that takes us to definition 2.5.2a and b. Limits at infinity are just that. When we are trying to find the limit of a function as our x approaches infinity. Now remember, there are two directions to both of our number lines, whether it's the x-axis or the y-axis. So that means we can go to the far right, which would be positive infinity, or the far left, which would be negative infinity. And yes, we can be approaching some number from both sides. Now, it's a little weird with infinities because that's not something that we can touch or hold. It's just an idea of the furthest left or the furthest right that you can possibly think of. So we say that there are limits at infinity when we are finding a limit by approaching either positive or negative infinity. So the interval that we would be looking at is from some number to the far right or from the far left to some number. And again, we always read these things from left to right. So if you look down at the bottom, what do you think graphically would happen if we were to have one of these two scenarios from the far right or the far left that we're approaching some number? Give you a little bit more time to think about that. What would we have graphically if either of those things are true, where our y value approaches some number when we go to the far right or the far left? Did you come up with it? It would be a line where our y is equal to that L. They're already stating that, and it's called a horizontal asymptote. So again, this is the process of having limits at infinity. Whether that be positive or negative, that just means to the far right or the far left. And if our y values approach some number, then we will have at that number the line y equals L, called a horizontal asymptote. Okay, something that we've seen before. And what kinds of functions? Do you remember the exponential functions? Looked a little something like that. What if I gave you that problem? And I told you that this was the function or the equation y equals 2 to the x. And I wanted to know what happens as x goes to negative infinity. Would this thing keep going down lower and lower and lower to where it actually crosses the x-axis? Well, no, it actually flattens out. And so therefore our answer would actually be 0. And we would have the asymptote y equals 0. But let me show you why algebraically using the thing that we talked about quite a few times throughout this chapter called direct substitution. Check it out. What if we directly substituted in what our x is approaching? Well, that would give us this, 2 to the negative infinity. And we know that anytime we had a negative exponent, we always took that thing and moved it to the opposite side of our division bar. We did the reciprocal, which I can say is 1 times that. So now I got the 1 up there still. And then this moves down to the bottom. And what is 1 over 2 to the infinity? 2 times 2 is 4, times 2 is 8, 16, 32, 64, 128, 256. You see, it's doubling every time. And if we have to do that an infinite amount of times, what happens to that number in the denominator? Well, it gets really large. And that's the symbol we use for really large. And what happens when we have 1 over a really, really, really big number? Well, there's 1 over 1,000. You know, that's 1,000th. That's really small. But what if I kept doing this? And kept doing that because it goes to infinity. What does that mean that this is approaching? Well, 1/10 is small, 1/100th is smaller, 1 whatever that is really small. And so it's approaching the number 0, as we can see. So that is our segue into this next part here that we're going to be talking about some quick rules. We want to be able to do this as quickly as possible for any rational function and limits at infinity that yields our equation of the horizontal asymptote. There are basically three scenarios that can happen. Of course, there's more, but we want to generalize this. So we're going to just look at three and not every. Here's the dot, 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 which represents and so forth. So if I had a polynomial on top and a polynomial on bottom, and of course in descending order, maybe skipping a power and all that, but I'm looking at the degree on the top and the bottom, the highest exponent. And if they are the same, or if the top is one bigger than the bottom, or vice versa, the bottom is one bigger than the top. And of course, it could be two bigger or four bigger, but what we're looking at is just a generic way, just one bigger, because that's the minimum it has to be. It can be more, and it will still hold true. Well, let me prove to you guys what these are by showing you and introducing something that I've mentioned a few times in this class, a lot in other courses that use it even more, but one of the most important concepts in all of math, and that is multiplying by a fancy one. Let's start with the first one, no pun intended. And let's say we had that scenario with, again, all the other stuff, but I don't really want the other stuff. I'm just going to write it down just to show you what happens and why we don't need to worry about it. So if I have my big old nasty polynomial on top and same on bottom, whether they're skipping any or whatever, goes from x to the first all the way on down to no power, which means it's just a constant, whether it's e, h, whatever. What we're trying to do is see what this would approach as we went to either the far right or the far left, positive or negative infinity. And I told you all we are going to do is take this and multiply by a fancy one. Now remember, you can write one easily, a little bit more involved, or whatever you wanted. I'm going to write it like this, and I'll explain why. 1 over x to the n over 1 over x to the n. And you know anything divided by itself is just a 1. So this is my fancy 1. Now, why am I doing that, and how did I choose it? Well, as we just saw, whenever we have something over a really big number, it's going to approach 0. And I like when things go to 0 because it wipes things out, all of that part of that term. So what I'm going to focus in on is making sure that I don't get a 0 where in this rational function on the bottom. And the reason we don't want to get a 0 on bottom is because if we wipe out all of this and it goes to 0, I don't care what I get on top, whether it's that or 0, or we cannot divide by 0. And we just did ourselves a disservice, because does it not exist? Does it exist? I don't know, because I don't know how to divide by 0. So what we're going to do is focus on whatever the highest exponent is in the denominator only. We're not even worried about the top because we don't have problems with zeros on top, only with zeros in the denominator. So I'm choosing this, and I will forget about all of this. Let me show you why. Let's actually multiply, distribute this through to everything on top and bottom. And that would give us, and if we multiply through that, 1 over x to the n, in other words, divided x to the n to every term on top and every term in the bottom, we can now do some canceling, some simplifying on all of this, which would give us, and now that I've divided out the x to the n to everything on top and bottom, canceling out all of them here and here, all of them but one, because this had one more than that, and so on and so forth down the line. Now I can try to accomplish my goal and see what my x's are approaching to either the far right or the far left. And again, we just reviewed what happens when I have my x approaching an infinity. Well, then this would become infinity, infinity, infinity for all of them. Whether it was x to the n minus 1 or x to the n or just x, it's still really, really, really big. It's infinity. If you have an infinity squared, still infinity. Really big. It's not something that we can touch, so I know it's a little confusing, but what did we say would happen whenever we had a number, C, D, E, F, G, H, whatever, divided by a really big number, such as infinity, all of those things would go to what? They would all approach 0. And we're okay with that because we are adding or subtracting all of these terms. And when we add or subtract nothing, we get nothing from them. And notice the only things that are left, that aren't zeros, that we were adding all of these zeros to, were the original coefficients of those highest powers or degrees of our numerator and denominator. So rather than having to do this ever again, which I will not, I just wanted to show and prove it to you why it is, we will see this, and given that, be able to know our answer is simply the A over B. Now you can probably guess that because these are different, it's not going to just be that for all of these. But if you're up for the challenge, pause it right here, do something similar to this and to that, and see if you can come up with the answers. I'll give you a few seconds to try that. Go ahead and pause it if you need more, and then we'll go over them and make sure you got the answers. Okay, hopefully you're able to come up with some of those, if not both. Here's the idea. Remember, we're evaluating these things with that direct substitution whenever we can with a limit. And remember, we said if it's rational or polynomial or trig or radical, all those different types of functions, exponential, logarithmic, inverse trig, as long as it's in its domain, it's all good. Well, that then, if we were to evaluate at infinity, it'd be infinity to the n plus 1 up here, and then infinity to the n. But if we canceled some stuff, what would we be able to cancel? You know, x to the n and x to the n plus 1 is going to cancel to have that plus 1 still. So we will have a to the x over b. And if we were to plug in infinity for our x's, then who wins the war? Well, you know, on top, they had more than the bottom. So they're going to win out. And therefore, since it's on top, we're going to have whatever a over b is times infinity, which means our answer would be either positive or negative infinity. Okay, and that's going to be dependent on the a over the b and what we're approaching. Okay, but what about number 3? Ax to the n over x to the n plus 1. Now who's got more? Well, that would be the bottom. And if we try to simplify that one, we'd get, and if we then plugged in our infinity for the x, now the bottom is going to go to infinity, which means our answer for this one would be 0. If you wanted to do it by multiplying by that fancy 1 to everything like we did on the first to these, you definitely could. That's how you would prove it. But for time's sake, I'm going to go ahead and leave that to you. If you have any questions on how to do that for these and why they're that, please reach out. We can go over it and make sure that we clarify. Otherwise, I got good news for you. There's just this last little theorem to not only wrap up the section, very short, sweet, but also for the entire chapter. Right? So here it is. We're going to generalize basically what we've been talking about since after that definition that we said is very technical and mathy. And that is, if we have a rational function where no matter what's on top, could be 1, could be any number, but if we have x to the power of r in the denominator, again, non-negative, so it doesn't move, but if we are approaching negative or positive infinity, then as long as we have a rational function of this type for our limit, we should know that whether you're approaching from the left or the right extreme, your limit result should be 0, approaching the x-axis, getting smaller and smaller and smaller as our denominators get larger and larger. Because remember, when you divide by a really big number, it gets small. So small that, remember, we're going to say it's approaching that value. And again, these will give us our horizontal asymptote. So to generalize, whenever dealing with rational limits, simply divide by the highest power, or we call that the degree And remember, we're only going to focus on the denominator to make sure that we do not get a 0 in the denominator and make it to where we can't evaluate that limit. So that's it, my friends. Hopefully you're feeling okay so far. I know it's new. Anything new is a little bit challenging, but with practice and extra time put in, this will definitely get easier and it will not go away. We're going to pause here and actually review for a little bit, make sure that we got this down before we take an assessment or test. So make sure that you work hard to tighten up anything that you're not feeling comfortable with. Come see me during my office hours. Go to our TA, use your classmates, help each other out. We're all a team here. Remember, it's us against the material. Coach Allen, signing off. I'll see you guys in chapter 3.